Hello guys, today we will discuss Vieta's theorem and prove this at first for the quadratic equation and then generalize for the n-degree polynomial. And in the end of the video, we will prove Newton's law. Vieta's theorem for the quadratic equation is that if we are given ax squared plus b times x plus c equals 0, and r1 and r2 are its solutions, r1 plus r2 equals to negative b over a, and r1 times r2 equals c over a. No matter R1 and R2 are complex roots or real roots. And now let's see why it is correct. If R1 and R2 are the solutions of the equation can be rewritten as a times x minus R1 times x minus R2. And if we expand this equation, we will get a times x squared minus R1 times x minus R2 times x plus R1 times R2. And multiply every term by a, we will get ax squared plus x times minus AR1 minus AR2 plus AR1 times R2. And as we know that these two equations are same, this means that the coefficient of every term must be same. So b times x must be equivalent of x times minus a times R1 minus a times R2. And c must be equivalent of a times R1 times R2. From here we can conclude that uh, b equals minus AR1 minus AR2. So R1 plus R2 equals to the negative b divided by a. And similarly, c over a will be equivalent of R1 times R2 if we divide both sides by a. So this is the formula of Vieta for the quadratic equation. We can easily use these formulas if we are given, for example, any quadratic equation. X squared plus 11x plus 30 equals to 0. Here we can easily see that r1 plus r2 must be equivalent of negative 11, and r1 times r2 must be equivalent of 30. And r1 must be equivalent of negative 5, while r2 will be negative 6. In this case, their sum will be negative 11, and their product will be 30, which means that our equation can be rewritten as x plus 5 times x plus 6 equal to 0. And these solutions are exactly minus 5 minus 6, and if we expand, we will get above. Now let's discuss what is generalized Vieta's theorem. In this case, if we are given p of x equals to an times x to the power of n plus an minus 1 times x to the power of n minus 1 and so on, all the way up to a0, and its solutions are r1, r2, rn. We will prove that sum of the roots, I changes from 1 to n, will be equivalent of negative an minus 1 divided by an. Sum of the pairs of roots, ri times rj, we are 1 is greater or equal, no, less or equal to I, and this is less than j and less than or equal to n. This will be equivalent of an minus 2 divided by an. And keep going like this. And similarly, we can compute the sum of the triples and so on. Last one will be product of every root, I changes from 1 to n, which will be equivalent of minus 1 to the power of n times a0 divided by an. And now let's see why it is correct. As we know that r1, r2, rn are the roots of the equation, our polynomial can be rewritten as an times x minus r1 times x minus r2 and so on. Here we may have repeated root, but it's not problem. If we want to compute the coefficient of x to the power of n minus 1, we just need to choose x in all of the brackets except 1. So this one can be rewritten as, the first coefficient is very easy to compute, an times x to the power of n. And second coefficient, coefficient of x to the n minus 1 will be minus a times r1 times x to the power of n minus 1 minus a times r2 times x to the power of n minus 1 and so on. All of the roots, sum of all of the roots. A times Rn times x to the power of n minus 1. Here we can see that coefficient of x to the power of n minus 1 will be minus ar1 minus ar2 and so on. And as we know that two polynomials are equivalent of each other if and only if all of the coefficients are same, this means that minus ar1 minus ar2 and so on minus arn equals to an minus 1. So this one equals to this value. So we get minus a times r1 plus r2 plus da 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 r to the power of n equals to an minus 1. And if we divide both sides by minus an, we will get r1 plus r2 da 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 rn equals to minus an minus 1 divided by an, which proves the first one, first theorem. Now let's see what will be the constant coefficient. If you want to compute the constant coefficient, we need to choose always Ri terms, R1, R2, and so on, Rn. And this constant coefficient will be an times minus 1 to the power of n times R1 times R2 times Rn, which must be equivalent of a0 because a0 was the constant term in the original polynomial. So product of the roots, R1 times R2 times da 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 Rn will be minus 1 to the power of n times a0 divided by an. And now let's see how to compute any middle term here. So sum of the t terms. So like product of t terms. In this case, this must be computed as, let's first show for Ri times Rj. If you want to find Ri times Rj, this means that we want to compute x to the power of n minus 2 coefficient. Because we are choosing only two roots and other chosen materials will be x. So x to the n minus 2 coefficient will be a times r1 times r2, because once we have minus r1 times minus r2, this will give us r1 times r2, plus a times r1 times r3, and all of the possibility of r1 connected to ri. So a times r1 times rn, and then keep going like this, a times r2 times rn, and so on. And clearly, this will be equivalent of sum of all of the pairs. And this must be equivalent of an minus 2 times x to the power of n minus 2. So this coefficient a to the n minus 2 will be equivalent of this value, an times sum of the pairs of the product of pairs. So an minus 2 will be equivalent of a times an times product of ri times rj. Yeah, I changes from 1 to n, and j is greater than 9. So we will get that product of the sum of the product of pairs will be equivalent of an minus 2 divided by an. Similarly, if we want to compute the sum of the product of triples, in this case we just need to compute coefficient of x to the n minus 3, because once you compute coefficient of x to the n minus 3, in this case we have to choose three terms which includes ri, rj, rk. So like this, an times r1 times r2 times r3 plus an times r1 times r2 times r4 and so on. R1 times R2 must be paired with all of them, and similarly R1 times R3 and so on. This way, this will give us the coefficient of x to the n minus 3, which was an minus 3. So these two numbers must be equivalent of each other, and we will get that an times sum of the product of triples, one is less or equal to I, less than j, less than k, less or equal to n, ri, rj, rk, this equals to an minus 3. So our sum will be uh, we need minus here because we have three terms which are negative, and their product will be also negative. So sum of the product of triples Ri, Rj, Rk will be negative 1 times an minus 3 divided by an. And clearly, if we keep doing keep computing every coefficient, we will get same formula for every term. So ai divided by an minus I divided by an will give us sum of the product of I terms. So here I changes 1 to n, j is better than this. And now we will apply this generalized version of Vieta to prove Newton's sum. And what is Newton's sum? Newton's sum, SI, this assigns the product of the I powers of the roots. R1 to the I power plus R2 to the I power and so on. So first one, S1 equals just sum of the roots, R1 plus R2 plus da da da, Rn. S2 will be sum of the squares, R1 square plus R2 square, da da da, Rn square. Newton's sum is An times S1 plus An minus 1 equals to 0. This is first level Newton's sum. Second level is An times S2 plus An minus 1 times S1 plus 2 times An minus 2 equals to 0. This is second level Newton's sum. Third level is An times S3 plus An minus 1 times S2 plus uh, An minus 2 times S1 plus 3 times An minus 3 equals to 0. And keep going like this until n level. So like we get An times Sn plus An minus 1 times Sn minus 1 and so on. The last term will be n times A0 equals to 0. This is n level Newton's sum. And now we will prove each of them by using Vieta's theorem and inclusion-exclusion principle. The first one is just direct example of Vieta because here S1 will be minus An minus 1 divided by An. Now let's prove the second level. And second level tells us that if we divide every term by An, S2 plus An minus 1 over An times S1 plus 2 times An minus 2 divided by An equals to 0. So in this case, this sum can be changed as negative sum of the roots, Ri, and this one can be changed as negative, just positive sum of the product of pairs, Ri times Rj. And as we know that S2 is sum of the squares, we will get Ri squared minus sum of the Ri squared outside, because we have Ri squared twice. S1 is also sum of the Ri. And plus 2 times Rij equals to 0. And clearly, this is always correct because once we expand sum of the Ri squared, this this expands like sum of the squares plus 2 times sum of the Ri Rj terms. And sum of the squares will be cancelled with this term, and Ri times Rj part will be cancelled here. Now we will prove third level, and after this generalize. So third level is that S3 plus An minus 1 divided by An times S2 plus An minus 2 over An times S1 plus 3 times A0, An minus 3 divided by An equals to 0. Once again, we will substitute this one as negative sum of the roots. This one is positive sum of the pairs, Rij. And last one will be substituted as negative sum of the product of triples, Ri, Rj, Rk. So we will get sum of the cubes minus sum of the Ri times sum of the squares, square of Ri, plus product of Ri times Rj times just sum of the roots, minus 3 times product of Ri, Rj, Rk. We all of them are different. This must be 0. If we expand this term, we will separately take the terms which equals Ri cube, and this will be minus Ri cube minus Ri squared times Rj, where I and j must be different. If we expand this term, we will get Ri squared times Rj terms with positive mark, but we will have also 3 times Ri, Rj, Rk terms. And clearly, some of the cubes will be cancelled here. Minus Ri squared times Rj terms will be cancelled here, and uh, positive 3 Ri, Rj, Rk terms will be cancelled here. And so we will get exactly what we want. And we proved third level. And how can we prove any level of Newton's sum? If we are given an times Sn plus an minus 1 times Sn minus 1 and so on. This is last level proof. N times a0 equals 0. Once again, we need to divide everything by an, and we get Sn plus an minus 1 over an times Sn minus 1 and so on. And times a0 divided by an equals 0. The first one is just sum of the n powers of the roots, so Ri to the power of n, minus sum of the Ri times sum of the n minus 1 powers, Ri to the n minus 1, plus, and so on. We get n times product of all of the roots, equals 1 to n, Ri. If we expand the second one, we will get all terms like Ri to the power of n minus Ri to the n minus 1 power times Rj, where I and j are different. If you compute the next term, this was just uh, Ri square times, not Ri square, Ri times Rj times uh, Ri to the n minus 2 power. And while we expand this term, we will get exactly this kind of term, Ri to the n minus 1 times Rj, but also different option, Ri times Rj times Rk to the n minus 2 power, which will not be cancelled. So these two terms will be cancelled, but this term will be cancelled with the next term expansion, and keep going like this. And finally, as we did in the previous two cases, we are left like always one term will be cancelled like this, and last term of the second last term expansion will be cancelled with this one. And so we have proved our equation. Newton's sums are very useful because if we know that sum of any n powers of n numbers, so like I mean, if we compute first sum of the first power, second power, and all of them, we can uniquely define these n numbers because we can arrange the polynomial which will have these numbers as a root. And if we solve the polynomial, we will automatically find the uh, n numbers which will satisfy all of these restrictions. Newton's sum will be used with advanced topics like uh, calculus 1 or advanced Olympiad like Putnam or IMC. If you want to discuss any problem about Newton's sum or Vieta's theorem, please write in the comments, and don't forget to like and subscribe my channel.